and also for this nice introduction. Yeah, as Krista introduced, I'm going to talk about how to use some deep learning techniques to solve a climate economic model, and then to see how the uncertainty would affect the decision making in this model. So let me start by thanking my collaborators in this project. So they are Michael Barney from the ASU, Arizona State University, Buzz Brock from University of Medicine, Lars Hansen from U of Chicago, and Joe Huang from UPenn. So as you may see that all of them are from economics. So I'm the only one from the math side or financial mathematics side. I need to say that this is my first project in the economics, and I with applications in economics, and I really feel there's a difference between what I've done in the past and in this project. So in the past, I'm always interested in like developing some machine learning algorithms, and then sometimes we have some assumptions which can simplify the work a little bit, and when we develop the algorithm, we find some toy examples that we show that the algorithm works really the best. But in those like real problems, in particular in economics, there are some assumptions or model specifications that cannot be simplified. So you really need to work hard on your numerical algorithms to make it work for this concrete specific setup of your model. And you cannot expect that you propose a algorithm and it can work straightforwardly as you wish, and then you always need to try to twist it and then try to accommodate their special structures or special properties from a real world model. So this is something that I feel from or I learned from this project. And then the main reference here is our working paper. It's called a deep learning analysis of climate change innovation and uncertainty. So we put it on archive last year. So it's still a working paper, and hopefully we are able to submit it this year. Yeah. Okay, so let me start with some high-level description of this project. So here we aim to understand or to answer how the uncertainty from the model to influence the R&D investment in the green technology. And then to answer this question, we work with a novel and relevant climate economic framework. So in this economic world, we have like three different kind of capitals. We have the R&D capitals, which is the knowledge ones, and then the higher the knowledge capital, it helps to trigger innovation, which can enhance the green capital productivity. And on top of it, we also have the dirty capital. For example, you have some company using the coal, or they have to produce pollutions, they produce carbon emissions, and you also have the green capital. We can think about like a company using solar energy or wind energy, or like electrical vehicles, for example. And then in the analysis of optimal strategies, we want to encounter different type of uncertainties. The first one is the risks within the model. What the economics people refer to risks is basically the randomness from the model itself. And in later on, you will see that we are using like diffusion models. There's a Brownian motion appears in the dynamics. So that's what they call the risks within the model. So there are some randomness in the modeling. And we also here can consider ambiguity, or we also call it a misspecifications across the models. So this means that there are different potential models or different potential probability measures that considered in this model. And then you are trying to work in a worst case scenario where you are trying to see so what is the minimal that utility that you can gain out of all the possible parameterizations or all the possible probability measures. Okay, so how are we going to tackle this problem? We develop this is basically we develop a machine learning tools and to solve this general equilibrium model with high dimensionality and then with endogenous nonlinearities. So we think this is a good contribution to the econ finance literature. So to the econ finance field, there hasn't been a lot of work in the economics or in finance where people are using deep learning methods to tackle the model numerically. And we also think this is a good contribution to the dynamic decision theory, and then associated with GEM processes. Okay, so let me start with the modeling on the climate side. So the geoscience people suggest that to use some approximations that could simplify model comparisons instead of using the very complicated ocean atmosphere circulation models, which cannot be really embedded into the economic side. So then Matthew and his co-authors in 2009, they proposed such a model where the temperature anomaly will depend linearly on the cumulative emissions. So basically, the temperature anomaly is proportional to the cumulative emissions, and it's scaled by this parameter beta f. So the beta f has a special definition. It's called the transient climate response to cumulative emissions, the TCRE, and this measures the climate sensitivities. So the data science, geoscience people try hard to go from those complicated atmosphere ocean circulation models to those simple linear dependence, and then try to have a good estimate of the beta. And then later on, Pelma and Steven in 2019, they proposed a stochastic version of this linear relation, and they claim that stochastics will improve predictability from the climate science models. So from the climate science perspective, they also feel having this broad motion part, it's a better choice to accommodate those some error or some deviation that cannot be explained. Okay, and so in our work, we are going to use these diffusion models where YT is this global temperature anomaly. So this will play an important role later on in this damage function. And this calligraphic ET is the global carbon emission. And so following this linear dependence, we say the change in the temperature anomaly is proportional to this carbon emission, and then multiplied by the change of the TCRE, the time change is multiplied by the TCRE parameter plus some diffusion term, the noise term. Okay. And then from the IPCC report, they always they claim that, or they think that if this temperature anomaly is between like 1.5 degrees Celsius or to 2 degrees Celsius, then there will be a severe damage to the environment or to the world. So now next, let's look at a damage function, a stochastic model for the damage function. Okay, so we model this damage to the environment as a log quadratic functions. So the log of the damage, it's takes a form of linear of a quadratic function of this temperature anomaly. So YT is the it follows the diffusion process that we see in the previous stage, and it's a piecewise. It has a piecewise definition. So the tau here is a jump time. So at the beginning, the damage will have the relation of the first line, and as the damage anomaly increase and increase, then if it's reached this threshold, or in particular this interval between Y lower bar and Y upper bar, then there's a jump processes that is associated, and there's a possibility that a jump will occur, and then the damage function will have additional curvature, which has more severe damage to the environment. So it basically says that if your temperature anomaly reaches a threshold, then the damage will be more severe to the environment. But we do not know the value of this gamma 3 a priori, and there could be possibly different choice for the gamma 3 M. So here to model this uncertainty, we're going to use jump processes, and there's only like one jump. that could happen between the interval, and then there's a jump intensity ID that given by this form, so it's increasing in terms of the temperature. Okay, so it has the economic or climate a requirement that the more it's consistent with the climate intuition that the higher the temperature anomaly, the more likely you cause severe damage to the environment. Okay, so we have this exponential function which is increasing in y. And then once the jump happens, it reveals the corresponding gamma-3, the additional curvature to the damage function. But we do not know a priori what's the value for this until it happened. And then we was assigned some prior probability, which is high.
So can I just interrupt you? One question. So the damage is then really NT. So I take the exponential of this function.
Yes, exactly.
And so what is the meaning when, so this log NT can be negative as well?
Yeah, exactly. So we take the, we want the NT to be positive. So
yeah,
it's real meaning damage. You don't want the damage to be negative to the environment. And then the way that we make it to be positive is you take the log, which can be positive or negative. And then we will take
and is it in terms of, I mean, this is now a function of the temperature of the anomaly, so it is not really in monetary terms.
No.
So it is just a measure and you have to convert it somehow in money then, I guess, or...
So later on, we're going to skew the consumption or the consume, what we consume from the economic side by this damage function. So you divide the consumption by this NT.
Okay.
Yeah, okay. So it's not like you subtract it from the consumption, which you have to have the monetary unit. Yeah.
Okay, thank you very much.
Well, thanks for the question. Okay, so then notation wise, we say this tau is the jump time, and then the y tau is the realized jump value. So then this piecewise function is actually like continuous. It's just as the temperature anomaly becomes more higher and higher, you have this additional quadratic term which having more curvature in the damage function. Okay, so we think that this modeling is novel in terms of it gives involves uncertainty about the future climate damages, and previous research always consider the NT is a deterministic or static damage function, so NT is a function of y or some other processes, or the uncertainty is never reviewed or never considered. And we also want to mention that a similar model is also was also considered in some previous work from my co-authors. Okay. And then here's a plot or a visualization about different possibilities of the jumps. So the right part is where a possible jump occurs at 1.5 degrees Celsius, and then compared to the possible jumps which happen 2 degrees Celsius, and then this shaded area is the possibility that damage outcomes across different choices of gamma-3. And then this solid line is the average about all the possible outcomes. And we will see that the earlier the damage happened, the more uncertainty it may have in the future. Okay, so now let's look at the economic side. So the previous two slides, or the previous two relations, they are about the climate models. And for the economic side, we want to talk about how the economy produce and what's the social planners' preferences and how it contributes to the emission. So in the climate part, we consider two sectors, the sector D and the sector G. D stands for dirty capital and the G stands for the green capital, and they follow the AK model. So I will talk about what is the AK model in a second, but basically the K here stands for the capital for the sector J, and it's driven by it's modeled by a diffusion process, where here the I is the decision or the strategy of the sector J. So how much money the sector J wanna invest in this capital in this sector, and phi is the adjustment cost. Here we are going to use the log adjustment cost, where alpha is usually interpreted as the depreciation rate, and then gamma is some concave function to make everyone has the problem to be well defined. So you cannot have really a linear growth or quadratic growth where your model will goes widely and then it can go to infinity. Okay, and then so you have two sectors, KD and KG. And then for the social planner, he's going to maximize his expected lifetime utility, the utility from 0 to infinity of the consumption over the damage. Okay, so you have the C tilde, which is defined to be the ratio between the consumption over the damage. So that's why we do not require the climate damage to be in the monetary sense. And for this consumption, we need to satisfy the aggregate output constraint. So that means so you want the part that you consume plus the part you invest in the dirty capital plus the part that you invest in the green capital plus later on the part that you invest in the knowledge capital. So we'll talk about what is the IK later on. That equals to what you output from the economy, which follows the AK model. So here is how the AK model looks like. So the output is proportional to the capital, which a parameter A, and then this is the A is called a productivity. So the output here is the summation from the output of the dirty capital and the green capital. Okay. And then here, when we are set up the model, we do allow for the disinvestment. So when we are searching for the solutions, we allow those investment to be less than 0. So that means like a disinvestment. Okay. And then among these two sectors, D and G, only the dirty sector will generate emissions, and this emissions is proportional to the output of the sector. So AD is output, the productivity multiplied by the capital, which is the output of the dirty sector, and then multiplied by a constant eta. So all those parameters here are really later on we have estimations from the real data. So it's not like for the numerics we assign some parameters that we like and then we solve the problem. It's not like that. Some of the parameters are extremely small and is very sensitive to the numerical method. Okay, so such a model is. So for these models is that the emission will be persistent. So once we emit to the atmosphere or to the environment, it will has permanent climate impacts. And this is very consistent with the concern expressed by the paper in Roscat in 2021. Okay. So we already talked about the capital from the dirty sector, from the green sector. So now let's talk about the knowledge stock. So there's another the part in this framework which we call the innovation. So kappa here is the knowledge stock, and this also satisfy model by a diffusion process where I is the investment in this particular capital. And then the higher the knowledge, the higher the intensity that there's a technology shock. And the technology shock, what was the purpose of this technology shock? The technology shock, first of all, it's a single jump, so it only happens once. And then this, when it happens, it will shift the productivity of the green capital to a higher level. So you go from the AG, which is the productivity of the green capital initially, to something we denote by AGJ. And so this is also something that we do not know a priori. So we model it also using a gem process with J absorbing states. So each state corresponds to a different AGJ and also give with prior distribution pi GJ. Okay. And then from the economic setup, at the beginning, we assume that the dirty sector has a higher initial productivity. So that means AD is higher than AG. But then when after the technology jump or or the post-tax the post-tax shock productivity for the green sector will be higher than the dirty sector. So to summarize, the relation between this AD and AG is that the post-jump productivity for the green is higher than the productivity of the dirty, and then it's higher than the productivity, the pre-jump productivity of the green. Okay. So all those parameters later on will be carefully chosen, and then to satisfy some to follow the economic that data. Okay, cool. So then this is all about the models. So we have two slides from the climate side. We have the damage temperature anomaly, and then we have the damage function. And then for the economic side, we have the three capitals, and then here is the utility function that the social planner is going to optimize. So at the abstract level, or to summarize the model from the control theory, from the control theory perspective, then essentially the social planner is trying to find optimal investment strategies, which are denoted by the I kappa, the investment from the knowledge, the ID, the investment from the dirty capital, the IG, the investment from the green capital, that maximize the planner's discounted expected utility, which depends on the capital of each sector, the temperature anomaly, the which is part of the emission, and the knowledge capital, and also the damage. Okay, so then how are we going to tackle this? We write the AJB equation using dynamic programming principle, but because there are several stages, then there are different sets of AJB equations. So the first one is the post-damage and tech jumps equations. So after the damage and technology jumps occurred, then it's a pure control problem. And then we denote the solution to be the V, M, and J. That corresponds to after we realize the value of the gamma, which is this additional curvature from the damage, and the that productivity, the new productivity of the green sector. Okay, and then this the value the AJB equation for this value function is self-contained, so we need to solve this one first. And then after we solve this, we go for the intermediate jump AJB equations. So the VJ will it represents the value function of the social planner, given that the tech jump has occurred and the AGJ has been realized, but the damage jump hasn't occurred. So that means the temperature anomaly hasn't been so severe that this additional curvature, additional second term is added to the damage function. And then the AJB equation of the VJ will depend on all the post-damage, post-tech jump equations. And similarly, we have the notation VM. So this is the AJB equation for the social planner, where the damage jumps already occurred, and we already know the value for gamma 3M, but not the technology jump. So we do not know, we are still expecting, or we are still hope to have a tech jump in the future, and then to review the possible value for AJ. And then in that case, your V will also depend on VM, or also depend on post-damage, post-attack value functions. And then after both of them are solved, which can be solved in parallel, because the VJ and VM, they are not coupled with each other, and then we can write down the we write down the AJB equation for the pre-damage, pre-tech jumps, which we denote by capital V, and then this will depend on the VM and the VJ. So I didn't put all the AJB equation in the slides because they are pretty long, and if you're really interested, then you can go to our working paper, and they are all in the appendix for different set of the AJB equations. But basically, for the numerical side, we need to solve the VMJ first, and then solve VJ and VM could be done in a parallel manner, and then we solve the capital V in the end. Okay, and go to the next part. And now let me talk about how we incorporate uncertainty. So the first uncertainty is about the risks, which is essentially they refer to the Brownian motion that appears in the dynamics, and then that part we just do the expected utility of the utility of the consumption, and the other part of uncertainty, which they refer to be the Jam diffusion model specification, is explained in this slide. So for the diffusion part, so we consider maybe there's more than one probability measure for this Brownian motion, or it's actually the Brownian motion is not a standard one, but with some drift term, and then to have things to work in have a reasonable solutions or with bounded rationality, then we need to add some relative entropy term as a penalty if we have this uncertainty there. So basically, in the AJB equation, you will have a H term in addition, and then but you will penalize or you want to minimize this cost, which is interpreted as a worst case scenario, facing all possible probability distributions of the model. And then for the jump part, we introduce a positive function G, which multiplied by the black one. So without the uncertainty from the jump misspecification, in the AJB equations, you will have a term which is the intensity of your underlying process multiplied by this difference and then multiplied by this transitional probability. And then if by introducing this G function, then the purpose is that so that the when we optimize the G part, the distorted jump probability and the intensity will both be mathematically tractable. And then this is a framework proposed in a paper by Lars and Sargent in 2001. Okay, we are following their framework for the jump and diffusion misspecification, and in this case, the original utility maximization problem will have additional term, which is the relative entropy here that depends on G and H. And you can think about this as a two-player zero-sum game. So one social planner is trying to optimize the social fare, which is the exponential discount of the utility of your consumption. And then the other one is trying to minimize over G and H, and then figure out this worst case scenario and facing the uncertainty consequence. So here, the G and H, they are also chosen. So those are endogenously determined, and then to account for the drift and jump distortions. Okay. And then, so how does the relative entropy terms raise? So the G part and the H part, they are separated. The G part comes from the jump part, and the H part comes from the diffusion misspecification. And actually, both of them can be solved explicitly. And here we introduce this C as a preference parameter, and this measures the uncertainty aversion. So the smaller the C is, the higher the uncertainty aversion. And then we think the constructed worst case probabilities, they act as a uncertainty adjustments to the social planner's valuation, and they are trying to reflect the magnitude of their concerns. So in the numerical part, we are going to examine how those uncertainty from the damage distribution, damage arrival, or the damage jam and the innovation jams, and also from the climate models from the H that could alter or could change the decision-making process. Okay, so it's all so far it's all about the models and all about the equations, how the problem is reduced or translated into solving the AJB equations. So now let's look at how we do it, how we get the numbers out. So climate economic models or problems always require a combination of solutions. Given such a complicated and realistic models, usually you cannot expect to have some tractable solutions or analytical solutions. And And so then the people are usually look for some numerical resolutions. And then in our case, we have at least 4 dimension in our AJB equations. So what are populars? The popular like finite difference methods are no longer available, and the popular finite difference methods are popular in the economics world. And then in the past, there are many like problems or climate economic problems that has been solved in low dimensional and using finite difference methods. Okay, so here we are trying to develop a neural network solutions and try to solve these complex models. So only recently, those neural networks solutions has been applied to economics and finance literatures. And here is almost an exhausted list of the papers which contains the neural network elements. And for our methods, we are trying to improve the deep galaxy method with policy improvement algorithm for this nonlinear coupled PDEs. And so specifically, we are approximating both the value function and optimal controls by neural nets. So, but I mean, this is already done in the DGM PIA. And for us, we are trying to improve the accuracy first of all using the ResNet, and then that could accelerate the training quite a lot. And also, I think the most important contribution from the algorithm side is that we introduce the pseudo-state variables into the parameterization, which is critical in the algorithm in the sense that for the value function that we are aiming to solve, it has some monotonicity property in terms of some of the parameters in the model, and there are some economic interpretations that has to be followed. So, for example, for this damage parameter gamma 3, economically, the value function has to be monotonic or has to be decreasing in terms of gamma 3. So the severe the damage, the less the consumption the planner can get from this model. So this is something that needs to be satisfied, and then cannot be done by the original cannot be achieved by the original DGM framework. Okay. Go. So we think that we view our paper to be what's the contribution here. So we view our paper to be the first one to apply the neural network in the economics and finance to confront endogenous nonlinearity from applying the dynamic decision theory. And we are extending this paper by L. Aradi in 2022, which is about deep galaxy method PIA, and then also another paper from the economic side, we share a similar spirit. And we also try to apply some other already existing methodologies to solve our problem, to solve this super nonlinear, very sensitive model. And all of them failed. In particular, the standard DGM method failed because it cannot get the accurate solution. And I will mention why how we claim that. And then also for the extended DGM method, as we mentioned, it cannot preserve some monotonicity with respect to important economic parameters, which are very important from the econ perspective. So for us, we extended this DGM PIA by including those critical parameters gamma and xi as pseudo state variables. So xi is comes from the damage function. I mean, gamma 3 comes from the damage function, and then xi comes from this the preference, the uncertainty preference. Okay. We also want to mention that the pseudo states was already used in the past literature, but it was never used to try to improve, but never for the purpose of improving the algorithm accuracy. Okay. So then let me highlight our algorithms. So I will illustrate it using a very abstract version of the AJB equations. I don't want to write the fully write down the AJB equations fully explicitly, that will take really the whole slice here. So let's take the abstract version where V is just a value function and the X represents all the state variable. And the L alpha is the infinitesimal generator of the control process, and alpha summarize all the strategies, which is the ID, IG, and the I kappa. Okay, so for the DGM PIA, it solves, it aims to obtain the V and alpha simultaneously by parameterizing both the value function and the control. So there will be one neural network approximating V and one neural network approximating the alpha. And then those neural networks are updated alternatively using stochastic gradient descent. And how are we going to update these two parts? So it has a two-step procedures. The first step is you always assume that the control is given, and you try to solve this linear PDE. So basically, you are minimizing the PDE residual, or how you are trying to minimize the error from the PD operator acting on this neural network function, and then you want V theta to satisfy this PD relation as close as possible. And then the second step is that after obtaining an approximation for the value function, you want to find the corresponding optimal policy or the policy improvement from this value function that you obtained from first step. But instead of finding this pointwisely on the numerical side, we find it in the L2 sense or on the average sense, where nu here is a probability measure that you can choose a priori and to characterize the region's relative importance. So if you think that this specific region is more important to have a more accurate solution, or expect your solution to be lies in this region, then you want to sample more points here. Okay. And then numerically, everything here is approximated by its discretized version. So I think I don't have enough time, so let me skip the procedural code here. But basically, we are trying to replace those these loss functions by their discrete counterpart. Okay, so here's this part, and then doing some gradient descent to try to update the parameters. Okay. And here are some implementation details. So the algorithm is not very hard to implement. You can do it on Google Colab using PyTorch or TensorFlow, and it can be trained on most servers or even on a laptop. And here are the running times. It's not extremely long. It takes about like half an hour for each set of the solutions, and overall it takes about less than 1 hour to train the final solutions. And for the post-damage, post-attack jump solution, it's actually a 3-dimensional problem, because you no longer consider the investment in the technology, because there's only one jump in the technology. After it happens, you do not expect to invest more as a rational social planner, because you know that you're not going to increase the productivity anymore. Then why keep investing in this capital? So in that case, you have a 2-dimensional control problem, and with a 3-dimensional state space, the finite difference is still is still working. And in this case, we can try to benchmark the solution with of the neural nets with the finite difference one. So as a sanity check, or as a first step, we compare those solutions, and we really work hard, try to have them to be coincide with each other. So even I would like to say that from the numerical side, even achieving this is not very easy, because some of the parameters that in the model are really small, and it's hard to train it to get accurate solution. Okay, and after this, we look at the intermediate jump solutions, and also the pre-jump solutions, and we have let me show some simulation results. So before that, let me show the parameters that we are using here. So beta here is the TCRE parameter, and this is we take the average from like 144 climate models, and for the possible curvature in the damage function, we take 5 different possibilities and detect the the productivity of the sectors are taken to be 0.12 and 0.10. Prior jump and after jumps, the productivity for the green capital is pumped to 0.15. Okay, and then we examine what happens if there's the missophistications in the jump processes and also in the diffusion part, and we compare two different scenario. So K equals is infinity is called a baseline case where the social planner is neutral and is facing his indifference between these uncertainties and basically facing a standard stochastic control problem. And K equals 0.1 is another case where the social planner is really conservative and then cares about the uncertainty in the future. And all the remaining parameters, they are from the previous paper by Aberle and Wang, and also Bernie's previous paper. Okay, and then we simulate the trajectory, and in the economic side, they prefer to do the simulation without having the Brownian motion. Once they solve the problem, they prefer to simulate the trajectory without having the shocks. So all the plots here, when they are doing this, when they are plotting this, it's just a trajectory where you ignore the Brownian motion part. They just kill that and then produce this trajectory. So let's look at some of the plots here. So the first part is about emission. And we can see that in both cases, the baseline case and then the resensitive ones, the emission starts out similarly, and they increase over time for both cases. But it diverges and it's lower for the uncertainty case. Okay, so this really makes sense. And on the right-hand side is about the R&D investment as output of the as a percentage of the total output, and then with the uncertainty, the social planner tends to invest more at the beginning and to accommodate the unknown, to accommodate the unknown potential more severe damage in the future. But in both cases, we are able to see that the R&D is fairly substantial and ranging from like 1 to 3.5%. And just for comparison purpose, so this number is very reasonable. And there's some study on the R&D to the Manhattan Apollo project, which is about like 2% in the past. So such a small percentage is reasonable. And we can also see that both of them, no matter whether it has a baseline, it's a baseline of model, or it has a more concern for the uncertainty, the R&D is start to decrease as time goes by. And this is mainly because after a while, we didn't expect after the jump occurs, or after it reveals how the jump will look like, then the investors, the social planner does not have that much concern to hedge this damage risk, so they try to reduce the R&D investment. Okay. So then we also try to plot the investment on the dirty capital and then the investment on the green capital. And again, the red line is from the baseline, and then the green is about when K equals to 0.5. So we have several observations here. So first of all, we can see that the level of the investment in the green capital is much higher than the one in the dirty capital. So at the beginning, it's almost like 50% higher, but as time goes by, the green capital start to increase and the capital start to decrease. So it's about like 4 or 5 times compared to of the green one compared to the dirty one. And then the second observations is that the green investment persistently increase during the simulation, while the dirty ones begin to taper off and then damage over the time. And finally, we also see that uncertainty concerns leads to initially a higher dirty capital investment, but it decreases more rapidly in the uncertainty neutral case. Okay, where there's only a slightly amplification of the green investment due to the difference in uncertainty aversion. Okay. And then the next plots can help to explain why the planner responds the way they do. So here we have the plot of the distorted probability of the damage models. So remember that at the beginning, we assume a priori pi for a different scenario of gamma, and then this corresponds to the red plots, and then the posterior ones are obtained after we solve the G function, and then they are plotted in the blue shaded histogram. And so for comparison purpose, we can see that the planner adjusted this probability to keep more weights to the right end of the distribution, where the implied level of the damage change, the damage jumps are more severe. Okay, so the planner has, it means that the planner has an increased incentive to move away from the dirty capital towards the green capital when they concern about the model uncertainty. Okay. And then the last part is about this distorted jump, a distorted probability of the attack and the jump trajectories. So we can only see like a small adjustment to the jump probabilities of the damage. So the red line and the blue line are pretty close to each other, but the uncertainty was planner significantly downweights the probability of a technology jump occurring when they incorporate concerns about a model uncertainty. So we think that this highlights how the optimal endogenous response by the planner for determining like robust policy is to focus their model uncertainty concern on the technology jump. Okay, so then at the end, I wanna just briefly mention that so those are the parameters we use in order to solve the model. So you can see that some of the parameters are really small, in particular for the depreciation rate from the capital part, and the gamma 1, gamma 2, those are the damage function. The parameters in the damage function, they are really small. So, and also the beta, which is the TCRE parameters from the climate side, they are like 1.86, 10 to the negative 4, and also this zeta, which is the noise from the damage. So all those small parameters present a challenge in terms of getting the solutions numerically. And on top of it, we also want the solutions to be like monotonic in terms of the gamma 3 and in terms of the C. So in order to do so, we really try hard and try to improve the algorithms so that we can obtain the result that I present in the previous slides, and which are reasonable and consistent with the economic intuition. So let me try to summarize here. So in this work, we analyze a general equilibrium framework, and then try to use decision theory to evaluate the impact of uncertainty on climate policy outcomes. So we find that the tech innovation is the most important uncertainty channel. It played the most important roles here, other than other uncertainties that we introduced in the model. And here we take into account both the uncertainty optimal policy in our framework, and we feel that it relies heavily on the investment in the R&D. And it also, and we're trying to reduce the dirty investment. So on the numerical side, our contribution is developing a numerical deep learning algorithm to solve the nonlinear high-dimensional coupled PD system, and which has consistent economic interpretations. And we hope that our toolset will open a door to richer models in the economic side, and in particular in the uncertainty analysis. And there are some ongoing work. The first one is actually in the numerical results that I'm presenting, we only have one AGJ, and I denoted by AJ prime. So there's no like misspecification that considered in the TAC in the productivity post jump. And so we are trying to add these components in the computational part as well. And then the second part is, can we have some error bounds for the algorithm that proposed? So this is particularly of my interest of whether we can develop some error analysis for this DGM PIA model. Okay, so I think I will stop here, and thank you for your interest. Thank you for coming. Thanks.